High absorbency cellulose acetate electrospun nanofibers for feminine hygiene application. Menstrual hygiene is an important issue for every woman, as poor menstrual hygiene increases the vulnerability toward reproductive tract infections. Feminine sanitary pad is an important disposable absorbent hygiene product. Its functions are to absorb and retain menstrual fluid discharge and isolate it from skin along with maintaining comfort, preventing odor, and staying in place. Absorbent core keeps the desired absorption capacity and is mainly made up of hydrophilic cellulosic fiber. And to improve the absorption capacity, some commercially available feminine hygiene products use superabsorbent polymers. Superabsorbent polymers are materials which can absorb and retain huge amounts of aqueous fluids. For example, the average diaper containing superabsorbent polymers can absorb 30 times its own weight in bodily fluids. This type of polymers are also used in feminine hygiene pads and liners and other applications, including agricultural use. Superabsorbent polymers are commonly divided into two main classes: synthetic or petrochemical based, and natural or polysaccharide and polypeptide based. The superabsorbents available in the market today are mainly based on cross-linked sodium polyacrylate gels, which increase the liquid absorption capacity and liquid retention, thus allowing the product to be thinner with improved performance. However, there are some harmful chemicals present in this type of products. For example, the use of dioxins to bleach the cotton, which is responsible for side effects in the body such as pelvic inflammatory disease. Superabsorbent polymers are petroleum-based products and therefore do not degrade easily in landfills. Their use is not eco-friendly. Therefore, the authors of the paper fabricate cellulose-based nanofibers and suggest their use as absorbent core in feminine hygiene products, due to nanofibers possess increased specific surface area in comparison to microsite fibers. Electrospinning is one of the simple and cost-effective methods used to synthesize fibers with diameters ranging from 10 nanometers to 10 micrometers. Electrospun fibers possess characteristics such as high surface-to-volume ratio, tunable porosity, and flexible morphology with controllable diameter. In literature, cellulosic fibers have been used for absorption of water and other aqueous fluids. Cellulose derivatives such as cellulose acetate is biocompatible, has low cost, and can be recycled in environment by biodegradation. The authors of the paper preparate electrospun nanofibers of cellulose acetate with and without SPA encapsulation. Were synthesized and characterized in terms of their surface morphology, mechanical properties, and comfort. To demonstrate their use in female hygiene application, different tests such as free absorbency, equilibrium absorbency, and percentage residue were performed in different mediums, such as distilled water, saline solution, and synthetic urine. The results obtained were then compared with some of the now commercially available feminine sanitary napkins. Polymer solution preparation with and without SPA. For the experimental part, the authors prepared 3 different solutions of cellulose acetate, 2 of them with SPA. For the first solution, cellulose acetate was dissolved in a mixture of acetone and DMA to make 16 weight% solution for electrospinning. In 2 other formulations, 5 and 10 weight% solution of sodium polyacrylate were prepared by mixing SPA in methanol and then added to the prepared cellulose acetate solution in 1:1 ratio. For a better understanding of how nanofibers were made, I will give a brief explanation about electrospinning. Electrospinning process uses high electric field as driving force to draw fibers from electrically charged polymer solution. The basic setup of electrospinning consists of a syringe pump, voltage source, and a collector. To get continuous uniform nanofiber or design morphology, electrospinning parameters were optimized. These were feed rate, voltage applied, tip to collector distance, and needle diameter. The surface morphology of the electrospun nanofibers were observed by using field emission scanning electron microscopy, and the surface morphology of the absorbent core of selected commercial feminine sanitary napkins was examined just using SEM. Some image of sample S1 is shown in figure 2a, where fibers have a flat ribbon-like shape with an average diameter of 28.5 plus minus 5.6 micrometers. Electrospun nanofibers, as shown in figure 2b, were long and continuous, and uniform with average diameter of 111.9 plus minus 88.3 nanometers. Solution of cellulose acetate with 5 weight % of SPA was in suspension, and its effect can be observed in the form of partially pitted fibers. Number of pitted fibers increased on increasing the SPA concentration to 10 weight %, as shown in figure 2d. However, in both cases, fibers were long and continuous. The specific surface area and pore size distribution were determined by BET. As we can observe, the decrease in surface area and total volume for CA5 and CA10 samples may be attributed mainly due to the increase in fiber diameter and change in morphology from bit-free to beaded fibers. Total pore volume for commercial samples was also significantly lower than any CA-based nanofiber samples. Anti-electrospun CA nanofibers showed the highest porosity of 95.6%. This test was done to quantify the absorption capacity of sample with respect to time. As shown in the chart, it's clear that in saline solution and synthetic urine, the absorption capacity of electrospun CA nanofiber was significantly higher than any of the commercial products. In case of distilled water, CA nanofibers showed large absorption capacity as compared to all samples, except two commercial samples, S1 and S2, which were primarily based on only superabsorbent polymer. This test was conducted to determine the total amount of superabsorbent material or residue lost from the matrix after it reaches equilibrium absorption. Samples were kept immersed in known amount of distilled water and allowed to reach equilibrium absorbency along with the mechanical shaking for 24 hours. Electrospun nanofibers of pure CA and with SPA have almost negligible residue due to nanofibers are strongly entangled. For other commercial samples, S3, S4, S5, and S6, whole cellulosic fiber matrix disintegrates due to mechanical shaking for 24 hours. Tensile tests measure the force required to break a sample specimen and the extent to which the specimen stretches or elongates to that breaking point. As we can observe in figure 5, there is a significant difference between the elastic modulus of electrospun CA-based nanofibers and commercial samples. Under dry condition, for S1, S2, S4, and S5, the modulus was much lower than CA nanofibers. In general, these results show that mechanical strength of pure CA nanofibers was more than any other commercially available samples. Comfort of the fabric was quantified in terms of flexural rigidity and surface roughness. Flexural rigidity is an important parameter for the textile fabrics when used to support load without flexing, as is in the case here for sanitary napkins. As we can observe for CA-based nanofabric, the ability to absorb load without flex is significantly higher. Higher value of flexural rigidity for CA nanofiber sample make them more comfortable even as compared to commercial samples. Finally, we can talk about the conclusions. Only CA electrospun nanofibers show significantly large absorbency in all conditions, as compared to any other sample in saline solution and synthetic urine. Authors found that loading of SPA in CA nanofibers not only decreased the surface area and porosity, but also restrict SPA as well, resulting in decreased absorption capacity than only CA nanofibers. All the results clearly suggest that use of SPA or in general superabsorbent polymers can be eliminated if CA nanofibers are used to make the absorbent core in feminine sanitary napkins. This will not only reduce the health-related risks such as toxic shock syndrome linked with the use of superabsorbent polymers, but also make the disposable female sanitary napkin products more environmental friendly, as superabsorbent polymers are generally non-biodegradable. Thank you very much for watching this video until the end.